Warm greetings to everyone. I am Dr. Martina Jency, Assistant Professor, PG and Research Department of Mathematics, V.O.Chidambaram College, Thuthukudi. Today I am going to explain the Euclidean algorithm in number theory. So why we need Euclidean algorithm? If you want to find the GCD of two numbers a and b, first we need to list all the factors of those numbers and find the largest common factor. But Euclidean algorithm provides a practical method for computing the greatest common divisor of two numbers even without knowing their prime power factorization. So this algorithm is based on a series of successive divisions and the division algorithm. So first let us see what is division algorithm. Given integers a and b with b greater than 0, there exists a unique pair of integers q and r such that a can be written as bq plus r with 0 less than or equal to r less than b, where q is the quotient and r is the remainder when we divide a by b. Moreover, r is equal to 0 if and only if b divides a. For example, consider any two numbers. Here I have chosen 73 and 35. So if you divide 73 by 35, you will get the quotient as 2 and remainder as 3. So we can express 73 as 2 times 35 plus 3. Similarly, consider the other two numbers 120 and 30. Here 120 can be written as 30 into 4 plus 0. Here we are getting the remainder as 0. So we can express any two numbers in such a way. So here comes the Euclidean algorithm. Euclidean algorithm states that given positive integers a and b, where b does not divide a, let r0 equal to a and r1 equal to b and apply the division algorithm repeatedly to obtain a set of remainders r2, r3, etc. rn up to rn plus 1. So these remainders are defined successively by the relations r0 equal to r1 q1 plus r2, where r2 lies in the interval 0 to r1, and similarly we can define the other remainders r1, r2, etc. rn minus 1. Then rn is the last non-zero remainder in this process, which is known as the GCD of a and b. Here it is clear that each Ri is the remainder, and since Ri's are decreasing and non-negative, Rn plus 1 is equal to 0 at some stage. So the last relation Rn minus 1 equal to Rn Qn plus Rn plus 1 implies that Rn minus 1 equal to Rn Qn, since Rn plus 1 equal to 0. This relation shows that Rn divides Rn minus 1. Also, the second last relation is Rn minus 2, which is Rn minus 1 Qn minus 1 plus Rn. Since Rn divides Rn minus 1, and it is clear that Rn divides Rn, which implies Rn divides Rn minus 2. Similarly, we can say that Rn divides each Ri. So in particular, Rn divides R1 and R0. We know that R1 is B and R0 is A. So that means that Rn is a common divisor of A and B. So now to prove that Rn is the greatest common divisor, let us choose any other common divisor of A and B. Let it be D. So by the definition of R2 equal to R0 minus R1 Q1, which shows that D divides R2. The reason is we know that D divides R0 and D divides R1, since D is the common divisor of A and B. So it divides R2 also. The next relation shows that D divides R3. By continuing this way, D divides each Ri. So D divides Rn. Already we have seen that Rn is a common divisor of A and B, and we choose any other common divisor D, it divides Rn. This means that Rn is the greatest common divisor. Hence the proof. So here we have an example. By using Euclidean algorithm, we are going to find the GCD of 2689 and 4001. So here among these two numbers, the bigger one is 4001. So, by using the division algorithm, 4001 can be written as 1 times 2689 plus the remainder 1312. Again, express 2689 as 2 times the remainder 1312 plus 65. Similarly, you can express 1312 as 20 times 65 plus 12, and proceeding this way, we are getting 2 equal to 2 times 1 plus 0. So, the remainder is 0 now. So, choose the last non-zero remainder, which is 1 here. So, that is the GCD of 4001 and 2689. So, next comes the example. Finding the GCD of the numbers 42,823 and 6,409, and also here we are going to express it as a linear combination. So, the problem is find the GCD of the numbers and hence find the integers x and y to satisfy this relation. So, by using the Euclidean algorithm, first we can find the GCD of those two numbers. So, among these two numbers, the bigger number is 42,823. So, express this as 6 times 6,409 plus the remainder 4,369, and continuing this way, we are getting 289 as 17 times 17 plus 0. So, here the last non-zero remainder is 17. So, by Euclidean algorithm, the GCD of these two numbers is equal to 17. Next, to find x and y to satisfy the relation 42,823x plus 6,409y equal to 17, we do the reverse process. So, the reverse process is, in the previous page, we have seen we have expressed the number as BQ plus R. Okay. So, from each step you can write the remainder as example 17 equal to 2040 minus 7 times 289, and by the reverse process we know that 2040 is 6,409 minus 4,369 minus, and again we have expressed 289 as 4,369 minus 2 times 2040, and proceeding this way, we are getting the relation as 42,823 into minus 22 plus 6,409 into 147. So, we found that x is equal to minus 22 and y is equal to 147. So, if you want to find the GCD of any two numbers, even if it is large, by using Euclidean algorithm with less computation, you can find the GCD easily. Thank you.